So then one other thing that we commonly do with random variables is to talk about their expected value. So the expected value of a random variable on a probability space omega is gotten by over each outcome. We look at the value of the random variable for that outcome, so that's looking at x of omega 1, multiply that by the probability of that outcome, and then add all of those together. So this is the average of the values of x on the outcomes, and then they're weighted according to their probability. So let's suppose you've got a probability space modeling 3 coin flips. So here our omega is H, 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 where they're all heads, etc. And x is the number of heads. So for each possible outcome, we take the probability that it happens times the value of that random variable on that one. So we're looking at the probability that we get, H, 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 times the value of x for that outcome, H, 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 and then do this for all of the outcomes. So the probability, we've got tails, H, H, x of tails, H, H, etc. Hopefully you can continue this on from there. So then working this out, the probability that we get all 3 heads, that's going to be 1/8. And then our random variable is counting the number of heads, so we have that times 3 there. And then looking at tails, HH, that's still just happening 1/8 of the time, and then counting the number of heads there. We've got 2, and then continuing this on. So if you work this all out, you'll see that our expected value for the number of heads is 3/2 or 1.5. So that kind of makes sense intuitively that out of flipping 3 coins, that sort of on average we should get 3/2 heads, since heads and tails are equally likely for a fair coin. So this expected value is giving us, like, on average or in the long run, what this random variable, what values it will give. So you can also think about this as sort of the balancing point or average for the random variable. So I didn't list all the possibilities there, but if you had actually listed out all the different outcomes, there would have been 8, and that's kind of cumbersome to write that all out. So there are easier ways to compute the expected value. This one is, I think, much more common than the previous one. I'm not sure that this one is in your book, but this is really handy and a lot quicker if you have a lot of outcomes. Rather than having that many sums, you kind of cut it down. So instead of going by outcome, you can sort this by the possible values of x. So for each possible value for x, you add up x times the probability that x, the random variable, equals little x, that value. So the value times the probability that that value happens. So if we look at the probability space modeling 2 die rolls, once again, let x1 be the sum of the rolls. So looking at possible values for x1, those we could have 2, 3, 4, 5, 6, and then up to the biggest that we can get for the sum of the rolls is going to be 12 there. So for each of these, we're going to do that value times the probability that that value happens. For the value 2, we've got 2 times, and then the probability that we get 2. So we've got to think through this here for what the probability that that value happens. So the only way that that can happen is if they're both 1. So that's going to be 1 over 36 plus 3 times the probability that we get 3. So the number of ways, or the different ways that we can get 3 are as 1 plus 2 or 2 plus 1. So we've got 2 over 36 there, plus 4 times, and then the probability that we get 4, the possibilities are 3 plus 1, 1 plus 3, and 2 plus 2. So we've got 3 over 36 plus 5 times, and for 5, we get, let's see, we've got 1 plus 4, 2 plus 3, 3 plus 2, 4 plus 1, so we've got 4 ways there. And so on, so you can finish this up to actually compute the expected value there. If we consider 2 random variables, so they have to be on the same probability space here, so that's important. Then we can define their sum to be the random variable defined by, well, taking the sum of the values. Here this is on the same probability space that x and y were on. So for example, if we consider the probability space modeling 2 die rolls, like we have been, let x be the value of the first roll and y the value of the second roll, then when we look at x plus y, we're looking at the sum of the first roll and the second roll, so that's the sum of the rolls. So we just take the values of those 2 random variables and add them together. The expected value for this, it actually turns out that this is just the expected value of x plus the expected value of y. So this is a nice handy way to compute that if you've got the sum of 2 random variables. Similarly, we can also take a random variable and take a constant times that random variable and define that by taking that constant times the outputs, times the numbers that that random variable outputs. So for example, if x is the value of the first roll, then 2 times x, we get that random variable by just taking 2 times the value of the first roll. The expected value also works out nicely here, where the expected value of cx is equal to c times the expected value of x. So you can compute the expected value of x and use that to find the expected value of c times x. The product of random variables works out a little bit differently. The definition is along the same thing. We just take the product of the outputs there, the product of the values of the random variables, but it's not so simple with the expected value. It's not necessarily true that the expected value of xy is equal to the expected value of x times the expected value of y. This is a really common mistake. If you're not paying attention and being careful about this, make sure you do not make this mistake. So that does happen in some very special, or a very special case, which is if they're independent. So our definition for independent for random variables is that the probability that x is x and y is y for any value, any pair of values for those random variables. So no matter what values we're looking at for these random variables, the probability that both those values occur is just equal to the probability that x is x and that y is y, or times the probability that y is y. So this looks similar to our definition for independent for events, and that makes sense because here we're really just looking at the event that x is x and the event that y is y. And then looking at all the different possible values there, it should be independent for all of those values. And then if x and y are independent, the expected value for xy is equal to the expected value of x and times the expected value for y. So the proof of this is in your book if you want to go through that. But remember This is only when they're independent. So you can't use this in general. So a related idea to the expected value is the variance. So the variance gives a kind of measure for how far away from the expected value this random variable typically is. So how much it tends to deviate or how spread out the values for the random variable are. So the way we compute that, the first step is to compute the expected value. So now we're using mu as our notation for the expected value. And then you compute the expected value of the random variable that we can get by doing x minus mu and then squaring that. So by doing that computation using the formula that we had for expected value from before, you can figure out the variance there. So this might look kind of intimidating, but just sort of find your expected value and then use those formulas for expected value here on this part. So use those formulas from earlier on this part and then use that to compute the variance there. Once you have the variance, you can take the square root and that gives you the standard deviation. So the standard deviation is maybe the more common measure that people give for how big of deviations there typically are from that expected value. So there's one special distribution here that we're going to talk about that comes up all the time, which is a binomial distribution. So suppose we've got n independent trials of an experiment with probability of success p, and let the random variable x count the number of successes. So you can think about a coin flip here, that we're flipping a coin n times. It's not necessarily a fair coin. So if your success is heads, then that probability is p, and it might be 1/2 or it might be something else. So this is called a binomial distribution with parameters p and n. And so our example, flipping a coin n times, then in the typical case, p equals 1/2, or if it's not a fair coin, then p can take other values. And x is the number of heads there. Or you could consider it with the number of tails, that works just the same. For a binomial distribution, you can work out that the expected value of x is p times n, so just multiply those two parameters together, and the variance is p times 1 minus p times n. So those are handy where if you've got a situation where you've got a binomial distribution, you don't have to compute the expected value or variance, you already know them from those formulas. Alright, so that's it for this section. The next video will cover the rest of this chapter.